had to seriously consider.
Well, you know, you can, we have postdocs that don't go there.
Right, yeah.
In fact, now nobody goes there except these two people.
Right.
So it's a totally remote experiment. It's.
So I just put this online on YouTube, so people, when they come to the Institute channels, they know we are almost starting, but I mean, you still have a couple of minutes to go. So.
Okay, so we are live now already.
We are live now, yes.
Okay, I mean, I just follow instructions.
No, it's fine. I mean, we can keep chatting. I mean, just so
let me make sure I can find my talk.
If you like to.
Yes, I know I'm set up. It's okay.
Check.
I can
imagine.
Yeah, let me make sure that I keep my time here. So I actually adjusted this talk. I'm not quite sure how long it is, but it won't be more than an hour.
It's fine. I mean, I would say.
Don't worry.
Like, yeah, it's between 50 minutes and 1 hour. That's fine.
Yeah,
that's a typical.
Probably going to be closer to an hour. You know, you may be surprised, but I never give the same talk twice.
I'm surprised.
You should.
You are. I mean,
I cannot do it.
I'm surprised. Okay.
And so sometimes it gets better, sometimes worse.
I'm pretty sure it will be great.
So I was lucky because all I have seen have been very good, Francis.
But I always change some things, and you know, it's.
Yeah, I guess it's good. I mean, keep it. So we can talk about different stuff, right?
It's like teaching, right? It's
exactly.
You cannot keep repeating the same course.
Yeah. Exactly. It's much nicer.
So shall I try to share
please.
my screen just to make sure?
Yes, and then I'll say a few words in Portuguese, and then I'll present you. So,
you have to be careful because I probably understand, right?
I imagine so. So, okay. So do you speak apart from French? Do you speak any other?
Actually, I'm not seeing my. Let me stop sharing. I'm not seeing my talk. Myself.
Okay, we are seeing your email.
Yeah, my email. Okay, let me try again. Can you see my talk now? No, I have to share my screen again.
Okay, now.
Okay, you see it?
Yes, now.
Yeah, and now I go to, where is it? Oh, I should be able to make this larger.
Yes, on view, on the top right.
No, I know where it is. It's my mute button covers it. 1 second. I have to be able, okay, there we go. Is that better?
Perfect.
But it's not centered.
So
yeah, I have to, let me escape. This is strange. I've never had this before. Okay, I'm going to stop share one more time. I'm going to open it. Okay. Yeah, it's still off. Is it okay?
Yeah, it is.
Okay.
It is okay. I can see your mouse as well. So yeah.
Yeah, it looks okay to me. Ah, I see what it is. Yeah. Okay. Should be all right. I'm ready.
Okay, so I'll probably just make your presentation in Portuguese, then I'll make your presentation in English, and then I can start. So I'll just ask for 1 minute so I can speak in Português. Bom dia a todos, bem-vindos a mais um colóquio do Instituto de Física de São Carlos. Hoje a gente tem o prazer de receber o professor Francis Halzen para falar para a gente. Tá? Então eu gostaria de lembrar a vocês que, se vocês tiverem perguntas, por favor, as envie pelo chat do YouTube e ao final da palestra a gente vai repassar as perguntas para o Halzen e aí ele pode responder a vocês. Se alguém estiver desconfortável em escrever a pergunta em inglês, pode escrever em português, que eu tento traduzi-la da melhor maneira possível e repassar as perguntas. Então, agora eu vou pedir licença a todos, vou passar para o inglês para fazer a apresentação do professor Halzen e de maneira que ele possa começar já o nosso seminário. E gostaria de agradecer mais uma vez todos pela presença. So, good morning, everyone. Thanks all for showing up at this webinar. So, one more colloquium of our institute. So, today I have the real pleasure of hosting Professor Francis Halzen. So Professor Halzen did his studies at the University of Louvain in Belgium. I hope I got the name right. So then he moved to CERN, where he was a scientific assistant, and then he moved to the University of Wisconsin-Madison in the US, where he's now a distinguished professor. So he's a physicist. He works at the interface of particle physics, astrophysics, and cosmology. I guess he'll tell lots about it today to us. So he has a very nice record of doing nice experiments. So he was the principal investigator of the AMANDA, which stands for Antarctica Mobile and Neutrino Detector Array. So it was a first generation telescope in the South Pole to detect neutrinos. And now he's also the PI of the IceCube, which let's say is the next generation of AMANDA, which is now a kilometer scale observatory in Antarctic. So I guess he's going to tell lots about it today. So he's the leading force behind this very nice experiment. And also he has received many awards during his career. So just highlight two. I mean, he had a very nice career. So he got the Balzan Prize for astroparticle physics in 2015. And also in 2015, he got the European Physical Society Prize for astroparticle physics and cosmology. So Professor Halzen, it's really a pleasure to host you, to have you here, and please, the colloquium is all yours.
Thank you. It's thanks for this introduction. It's a pleasure to give this talk, especially to a place where I know there are people who are working on experiments that have similar goals to IceCube. So you have seen in front of you the menu for today. I'm going to talk about the beginning, give some brief introduction, talk about IceCube. Then I'm going to talk about the discovery of cosmic neutrinos. And then I'm actually going to go into a few topics where we think we are seeing, we are identifying actually the first sources of cosmic rays. And so neutrino astronomy fits in this picture where astronomers have tried to study the universe at different wavelengths of light, or for a particle physicist like me, different energies of the photons. So this is the microwave sky. It plays a role in this talk. Remember, there are 411 photons per cubic centimeter with an energy of 1/10,000th of an electron volt throughout the whole universe. This is a picture of the sky in light. That's what you see when you go out at night. And I will, when I show a picture of the sky, I will use this. And remember, the plane of the galaxy will be along the major axis. So you see here the plane of the galaxy and then sources outside. And this is the sky at GV energies. This is a picture taken by the Fermi satellite. And you see again here the sources in the galaxy and then some extragalactic sources, these little points there, which are mostly active galaxies. So now you say, let's just continue this. This is the sky at 1000 TeV, 1 PeV energy. What do you see? Absolutely nothing. This successful game astronomers play stops at some point. And the reason it stops is interesting. If you want to see a galaxy far away, it emits 1000 TeV photon. We actually know now they do, as I will emphasize, but that photon never makes it to your telescope at Earth because on its way, it's moving to this background of 411 microwave photon per cubic centimeter. What it will do, it will at some point interact, make an E plus E minus pair. And once you have charged particles, there is no astronomy because they are bent by magnetic fields in the universe and in our galaxy before they reach your telescope. Of course, this is why the cosmic ray problem is unsolved. They are charged, like they are mostly protons, and they are bent and don't tell you where they came from. So it's nevertheless interesting to continue. So here, this is the cutoff of astronomy. So there is this whole part of the sky, which extends to infinity, probably, that we have never seen. And it's an interesting part of the sky. It's occupied by cosmic rays. So we know there are sources there. In fact, we call them cosmic accelerators because they accelerate cosmic rays to these enormous energies. And so the goal is to study this hidden sky with neutrinos and hopefully find the sources of the cosmic rays. So neutrinos have been known as soon as they were discovered by Reines and Cowan. Everybody had the idea that you could do astronomy with them. And it's interesting astronomy because if we make a picture of the sky in neutrinos, you not only see the sources of the cosmic rays, you will only see sources of cosmic rays because you need cosmic rays to make pions and kaons to make neutrinos. So they track nuclear processes. And the problem is they are very difficult to detect. Now, here is the necessary picture of cosmic rays. They were discovered in 1912, more than a century ago. The lowest energy cosmic rays here at the top left of my panel come from the sun. And these are the highest energy cosmic rays that we know come from sources far outside our galaxy. And the interesting thing is that it's very difficult to even imagine where they come from, because they not only produce this very high energy, when you actually look at the luminosity of the sources, it's very high as well. So it's very difficult to imagine what the sources are. Now, I must admit, as a particle physicist, I'm in this business not to do astronomy. I remember when I saw the first time a 300 million TeV event detected by the Fly's Eye, a modest detector in Utah in 1991. And so we want to know how nature produces these things. And my friend Unger always reminds me, if they gave us LHC magnets, we would have to fill the orbit of Mercury to actually produce that particle. So given what I will tell you at the end of the talk, I'm going to give you an example of a cosmic accelerator. You're looking at a galaxy. This is a galaxy like ours. It has a black hole in its center, just like ours. However, this black hole is active. It's eating up its galaxy. It's eating star gases, molecular clouds continuously. And so the galaxy is being absorbed in this black hole, like in this whirlpool. But you imagine when these particles and magnetic field lines come close to the black hole, when what's called the accretion disk touches the black hole, by general relativity, it's rotating. It will drag the field lines and all the particles and wind them up. This is shown a little bit better in this plot. So the black hole grabs the field lines and the particles and wind them up in a jet that is perpendicular to the plane of that active galaxy. Is this really how it works? We don't know. There are other ideas. But we know from astronomy that we see this happening. So whether whether we got the details right or not doesn't really matter. The other thing you have to imagine is this doesn't accelerate particles. When this happens, it grabs blobs of plasma and throws them out along this jet, which explained why you not only can get high energy, you can also get very high luminosity. So what do neutrinos have to do with this? Well, here you see it. If you have a beam or these blobs of protons being accelerated along this jet axis, this galaxy is active, and so it's surrounded by light. And so these protons can interact with photons radiated from this galaxy, make pions, and the pions will decay if this in a muon, for instance, and a muon neutrino, and the muon will further decay in electron, a nu e and another nu mu. And so this is how actually we will try to identify these cosmic accelerators. This is not any different from what they do at Fermilab, right? You have an accelerator, which in our case is a supermassive black hole. You have a target nearby, which is the radiation here surrounding the galaxy. And then by 1950s physics, you make charged particles that decay into neutrinos, and you make pi zeros that decay in gamma rays. I told you, we have seen, as you will see, 1,000 TeV and more, 10,000 TeV neutrinos. So we know this galaxy produced 10,000 TeV gamma rays as well. So the real question is, how big a detector do you need to do this? And so theorists, including me, for a couple decades, started modeling possible ideas. But there, as I told you, there are not that many. So these are supernova explosions. Predict this gray band here. What I'm showing you is the flux of neutrinos. In fact, it's not a flux, it's the energy flux. You see this E square here. And so as accelerators, cosmic accelerators, we think, have a spectrum of 1 over energy squared. It's not a monoenergetic beam like at CERN. Then if I multiply the flux by E square, all my predictions line up here. This is a prediction of gamma ray burst, and this is an interesting prediction. It's the flux of cosmic rays interacting with the microwave background producing neutrinos. You know, just like I showed producing an E plus E minus pair in an earlier picture, they can also produce neutrinos. And so what this picture shows is that if you build a fully efficient 1 kilometer cube detector, then you will see here 10 to 100 events per year. And that was the goal, to do a neutrino astronomy, to build IceCube. This was our sales pitch for IceCube. The problem is that if you look up at the sky, you see a lot of neutrinos. They're made in the atmosphere. And so you see Amanda, which was mentioned in the introduction by IceCube, have been measuring this flux for years before we discovered cosmic neutrinos. So what you expect is that at some point, this flux disappears and it's taken over by a cosmic flux. This happens around 100 TeV. 10 to the 5 GeV you see here, this is 100 TeV, which I will use as my unit. So atmospheric below that, cosmic above that. So just to remind you, cosmic rays hit the atmosphere, they make pions on nitrogen and oxygen, and these pions decay and you know, make a continuous flux. If you look up at the sky, we see neutrinos, and lots of them, as we will see later. So how do you build a neutrino experiment, the big one? We know how to do this. You need water and phototubes, and it has been done in Japan. And the problem with the Japanese experiment, which is a marvel of technology, is that it's 10,000 times too small to have a fully efficient kilometer cube detector. So that's where IceCube came in. And it was not really our idea. The idea goes back to 1960 to Markov, who you see on the left of the picture. And these are his words, but I will read. Here is a cartoon of what he said. You go deep in a lake, or he was thinking of Lake Baikal or the sea, and imagine a dark kilometer cube of clear ocean water, deep clear ocean water. You instrument it with photomultipliers, and so you have some form of super K. Then what you do is you look through your feet and look for neutrinos coming up through the Earth. What will they do? They will just go through your detector. However, about 1 in a million at TeV energy will hit a nucleus in the water. And if it's a muon neutrino, it will make a muon. And this muon can travel through your detector. In fact, the muon goes at the speed of light, and it interacts with the water, making light that goes in the water at 3/4 of the speed of light. So it makes this shock wave of light that's produced by the muon. And if you map this shock wave, you can tell where the muon comes from and the neutrino comes from. That was Markov's idea. This was tried 1987 by a pioneering experiment doomed off the coast of Hawaii. Unfortunately, that experiment failed. And so we came in with the idea of putting the photomultipliers in ice instead of in water. And where would we do that? Well, we do this right at the geographic South Pole in the center of Antarctica. And the reason it's there is because you are standing here on 3 kilometers of water. It's a glacier, of ice, sorry. And the National Science Foundation has a research station there that can support the construction of the experiment. So here you see the research station on the left, where my pointer is now is the geographic South Pole. And this is the IceCube construction. In the middle, you see the runway where the planes land that bring everything into the South Pole, including your experiment. It took us a long time to figure this out, well, years, and we actually found this good news that below 1.35 kilometers, this ice is ultra transparent, and we hope that it could act as a Cherenkov detector. So you see here the simple concept. You go 1.5 kilometers deep and you will find a kilometer cube of ice instrumented with photomultipliers, with light sensors. And then you see here Markov's idea. We look through our feet to, and when the muon comes through the detector, it lights up the photomultiplier tubes. So again, 1450 meters, 5,160 light sensors, and in fact we are still more than 400 meters from the bottom of the ice here. So the photomultiplier tube, they are the size of a basketball, 10-inch, and that's the easiest part of the experiment. You buy them in Japan. And so if you could go inside the detector, you would see these kilometer-long strings of light sensors, and one every 17 meters, 60 per kilometer string. You go 125 meters away and there's another string. 125 meters away, another string. 86 of these strings make IceCube. So this photomultiplier has around its neck electronics. And what this electronics does, it digitizes the light that's detected. So this is the pattern of light, for instance, detected by a photomultiplier. The electronics digitizes it and sends it to the information to a computer at the surface over a cable that brings down the same cable that brings down the voltage to the photomultiplier. So there is no IceCube. You have 5,000 freely running photomultipliers, and the computers at the surface collect these images and put them together into neutrino events. Each of these images has a timestamp on it of 2 nanoseconds. So the detector, we can time the detector by 2 nanoseconds over 1 kilometer. So just one picture here. You can only work at the South Pole during 2 months. And so this particular 2 months, the IceCube project had drilled 20 holes. You see the cables come out of the ice. These cables go into this 2-story building, and this 2-story building houses about 300 computers. What does this, what do we detect? Well, as you can guess, we mostly detect atmospheric neutrinos and also atmospheric muons, because although we are 1.5 kilometers deep, the detector is so big that it still collects 3,000 atmospheric muons every second. So again, atmospheric muons from the southern hemisphere, from the back, neutrinos, atmospheric neutrinos from the atmosphere all over the Earth. And in that background, we have to find these astrophysical neutrinos. So here, in case it's still not clear, you see here atmospheric muon going through the detector. You see the Cherenkov light. This is the simulation. And you see these colored dots means that the photomultiplier detected light. And so each of these colored dots represent one of these waveforms, one of these digitized patterns of light that I've shown before. So here you see the detector taking data, and you see it collects these signals, and it continuously fits muon tracks to it. You see the picture repeat. At some point, you see a muon bundle going through here, right now. And so this movie is 10 milliseconds long. So what does that mean in the end? So if you look at a year of IceCube data, we have collected about 100 billion atmospheric muons, 3,000 every second. We collect by now, in fact, more like 200,000 atmospheric neutrinos per year, one every 4 minutes. And as you will see, in that huge background, we actually managed to find about 120. We know we have 120 cosmic neutrinos per year. Not all of these we can separate from this background, but enough to make the case. Now, here is a picture of how we do this. So here you see the top 90 meters or so is snow. So we just melt it. Then the hot water drill comes in, and the hot water drill is basically a nozzle that puts out boiling water under pressure and melts. There's no hole. It melts the ice over 2.5 kilometers. And this takes about 2 days. So what we have here is a 4.8 megawatt heating plant that puts out 200 gallons per minute at 90 degrees C and under pressure. And the whole system is mounted like a circus train, except that it's on sleds. This is the drill tower. This is the control of the drill tower. This is the 2.5 kilometer hose that goes in 2 days down to 2.5 kilometers to make your hole. These are 45 car wash heaters driven by generators and normal fuel. And that represents a 4.8 megawatt power plant. Here you see the drill at this point coming out of the hole. So there's no hole, right? We just have transformed ice into water. As ice is an insulator, that water stays liquid for a long time. And so we are just now going to put the photomultipliers in it. They are waiting 60 for this hole. There they are in boxes, in a pressure vessel, of course. There you see. And the pressure vessel is a 1 centimeter thick glass. And so you see now, these are the cables that are going to go to the 60 photomultipliers. And so this is the cable reel. You attach a photomultiplier every 17 meters and then let it sink in the hole. And that's, of course, the last time you see your photomultiplier. So that's IceCube. How did we discover cosmic neutrinos? Well, 2 ways. On the right is the classic case of a neutrino coming through the Earth, which Markov suggested. On the left is a method inspired by Super Kamiokande. You look for a neutrino that interacts inside the detector with no light coming in anywhere. And that's, of course, a neutrino. This is one of the events that was part of the original discovery. Here is the lake in Madison, and the data center is close to the Capitol. And I have superimposed the event I just showed. This is an event starting in the detector. And you imagine the size of it. It's about 5 city blocks wide, and more than 300 sensors reported a signal, so more than 100,000 photoelectrons that we can reconstruct to 2 nanoseconds. So you can imagine that we can reconstruct the direction and the energy of this event. This is the second time of event. This is a neutrino that comes from 11 degrees below the horizon, and its energy is so high that it's a 5 sigma discovery by itself, close to 5 sigma. It's this single event, because the atmosphere cannot produce neutrinos of this high energy. So in fact, this event, 2,600 TeV was deposited inside the detector. And then from standard model physics, you can estimate the most likely energy of the initial neutrino, and it's about 7,000 TeV. So we recently found this event, which looks like one more event, but actually we can prove that the energy of its initial neutrino is more than 10,000 TeV. So this is definitely a discovery of cosmic neutrinos by itself. So here, back to our 2 classical methods. So here you see again the number of neutrinos detected multiplied by their energy. So this is the energy flux. And here you see 100 TeV. Remember, this was the demarcation line. This is the atmospheric background, but we can separate the cosmic neutrinos from the background almost down to a few TeV. And here you see the measurement of the events starting in the detector. This is the Markov measurement. And where does that come from? It comes exactly from what I advertised. This is actually the number of neutrinos we detect as a function of energy. And when you come to 100 TeV, which is here, you see the deviation of the cosmic flux that we were supposed and did discover with a kilometer cube detector. That flux is represented by this pink line. Above, you see 100 TeV. The 2 measurements completely agree. And what you expect, this is a more recent update. You see again 3 different analyses. I won't go into detail. And the flux is not very well measured, but they are all compatible. And as these, we'll see in a minute, these neutrinos actually don't come from our galaxy. They come from very far away. And so by oscillations, we receive equal numbers of nu e, nu mu, nu tau, which is, we plot as a fraction of nu tau, fraction of nu e, fraction of nu mu. This is 1 to 1 to 1, and this is our measurement with a big error bar. We are trying to make this measurement more precise, and because this is an ideal way to look for new neutrino physics, of course, doing oscillation measurements at 1000 TeV energy. So I have told you how we discovered cosmic neutrinos with two completely different methods. So, but we actually have these individual events. I showed you already a couple, that convince us that we can see cosmic neutrinos. In fact, we found another method to certify this flux, and that's by measuring tau neutrinos. Now you remember tau neutrinos were discovered at Fermilab in an emulsion, and what you do is you look like in this picture. This is a neutrino interacting, producing a tau, and the tau decays, and the lifetime is of the order of a centimeter or so. Well, if you go to higher energy, this lifetime becomes longer and longer. And at 1000 TeV energy, at 1 PeV, this 1 centimeter has become 50 meters. And you see this event here. So what you will see is, this is a computer simulation, is a new tau interacting in IceCube and then decaying 50 meters later. Well, here is an event. You cannot really see the decay length is 17 meters, but if you look at light detected by the optical modules, let me look at the top right one here. You see here the characteristic shape with the first bump when the light emitted when the neutrino interacts, and here the second bump when the tau decays. And so we can, this event was found in 3 different analyses. And so that's another confirmation. Another event, I could go on for the rest of the lecture on this. This is actually an anti-electron neutrino interacting with an atomic electron. It's the only exception, it's one of the few exceptions where you can actually produce, a neutrino can interact with an atomic electron rather than with the nucleus. And that cross-section is very large. And unfortunately, the energy required to produce this event is 6.3 PeV, 6,300 TeV. So these events are rare because they're high energy, the flux is slow. But if we assume that this is a Glashow event and fit it, you see here the reconstruction. And we fit exactly the energy expected. And, you know, we got very excited about this, not because we had discovered, of course, what this electron then eventually produces, an 8HF weak intermediate boson. But we got not excited about the boson, but the fact that we measured its mass, its energy correctly. So this is a beautiful calibration from the detector. Where do these neutrinos come from? Well, here you see the sky map I promised. They are collected in different analyses. And the interesting thing is these are neutrino, the cosmic events that we really suspect to be cosmic, that we can separate from the background. And the interesting thing is that what you don't see. You're supposed to see first nearby sources in your galaxy. And I told you the galaxy in my sky map is the big axis, the large axis of this ellipse. Nothing. And so this map at that time, I don't remember, this is about 6 years of data, was completely uniform. Anything you may see in this map is consistent with the acceptance of the detector. In fact, to warn the theorists about getting excited about small numbers of events, this event here, come right from the center of the galaxy, is the first event we ever measured. So now there is no evidence that it's special. After 10 years, we just published our 10th year of data. After 10 years of data, for the first time, our map is not uniform anymore. It has some asymmetry in it, which is due to 4 sources. I won't go to this in detail. It's our 4 active galaxies. And one of them is TXS 0506. It's an active galaxy, which you will hear more about later. So the conclusion is we observe a diffuse flux of neutrinos from extragalactic sources. And the big question is, where are these 10,000 TeV gamma rays that accompany our 10,000 TeV neutrinos? And that's an interesting story. You see, I explained that 1950s physics tells you there is a pi 0 for every pi plus. And we have instruments that can measure these gamma rays. This is here magic in the Canary Islands will play a role in this talk later. They use the atmosphere to measure gamma rays, just like we use the ice to measure neutrinos by Cherenkov radiation of the showers they make. Another way to measure these gamma rays is to just deploy a gamma ray detector above the atmosphere. And so this is the Fermi satellite, or a model of it at Stanford. And you see it just converts gamma rays in electron-positron pairs and measures their energy and direction. So this is the classic multi-measure picture. So I complete a picture now for the pi plus I showed before. There is a pi 0, there is an electromagnetic shower. And I already explained to you, this shower will develop in the microwave background, and the photons will disappear. But of course they don't disappear. You have to conserve energy. This positron, for instance, will radiate. This photon will pair produce again on the same microwave background. And so what happens is that, yes, you don't get a 10,000 TeV photons, you get many GeV photons at Earth from the showering in the microwave background. So this is just QED. This is perfectly calculable. And that's what we did. Here you see an old version of our data that we fitted as a power e to the minus 2.15. Then you say there is an equal flux, an equal energy in gamma rays. You evolve these gamma rays in the microwave background, and you end up on the red line. And the red line is the extragalactic diffuse flux measured by the Fermi satellite. And so this was a big surprise, kind of. What it tells you is that, yeah, the gamma rays are there. They are just shifted to lower energy by showering in the microwave background. It's amazing, because the way I look at it, so the energy flux in the universe in neutrinos and gamma rays is the same. So gamma rays, in fact, it's also the same as in cosmic rays. So it means that neutrinos and cosmic rays are a part. They are not some boutique science that deals with exotic effects. They are part of the astrophysics structure of the universe at the highest energies. So we try to correlate the arrival directions of the neutrinos with anything you can think of for about 2-3 years, and we're totally unsuccessful. And then we tried something else. What we tried was to, starting 2016, was whenever the South Pole computers reconstructed a really high energy neutrino event, we sent, without further analysis, we sent the arrival directions of the neutrino to the astronomical community to a telegram. So we release our high energy, our best neutrinos actually, to the whole community within less than 1 minute. And on September 22, 2017, we sent this telegram with the arrival directions of a 300 TeV neutrino, very likely to be cosmic, coming from these arrival directions. And here it is. And it was soon realized that there was an active galaxy in the direction of this neutrino, and this active galaxy was observed by Fermi to have increased its flux in the last few months by a factor of 7. So it was flaring, which is a rather unusual event. And you see here, we at the neutrino pointed to better than 0.1 degree in the Fermi direction, in the galaxy direction. So this can happen by accident at a level of 3 sigma. What makes this a real convincing identification is what followed afterwards. This is interesting, but not conclusive. What happened afterwards is that MAGIC, a few days later, actually 5 days later, discovered that this galaxy was actually a TV emitter. And that's even more rare. So now the plots begin to thicken. In fact, we had no idea whether the astronomy community ever paid attention to our telegrams. Well, at some point, more than 20 telescopes were looking at this event. In fact, the first to discover TXS active galaxy was Swift. Here you see Fermi. There is MAGIC. And all these optical telescopes were trying to identify the whole host galaxy. This finally was done when the galaxy quieted down at high energy, and these people discovered 3 absorption lines and told us that this galaxy is at 4 billion light years, 1.7 kiloparsec, which was a real shock. It's not nearby, it's really far away. So that, however, is not the end of the story. So here is a summary of what happened, Fermilab, MAGIC, and more telescopes. But we now, knowing where to look, we can now look at our archival data without having to take the penalty and trials, the look elsewhere effect of having to search the whole universe. So we just go and look through our past data. So we had 9.5 years of data in that direction of the sky, which you see here. And you're probably all looking at the wrong thing now. This is what I have been talking about in 2017. This is what we saw in 2014-15. More than a dozen neutrinos, in fact 19 on a background of less than 6, with an e to the minus 2.2 spectrum and an enormous luminosity in neutrinos, close to the Eddington limit. If you don't know what the Eddington limit, it doesn't matter. It means it's big. And so this, you know, adding this to the accumulation of evidence make this pretty convincing. So this was, of course, the first attempt to do neutrino multi-messenger astronomy. And so we have a tool now, I think, to study and to identify cosmic ray sources. What's interesting with this source is at 10 times the distance of similar sources that are nearby, it outshines all the nearby galaxies in neutrinos. So, you know, there are, for the experts, the Markarian active galaxies, they are 10 times closer. They should have 100 times the flux. Why this one? So they must be, this source must be special in some way. And of course, because of this campaign, this is now one of the best measured sources ever. You see here its spectrum, not in neutrinos, in gamma rays. And astronomers call this source a blazar because the jet is actually pointing at the direction of the Earth. You see here in the detection in X-rays, gamma rays, and neutrinos. And these sources are well understood. The problem was when we applied the conventional astronomical blazar models to it, this model has 14 parameters, and we couldn't get one neutrino. And so this became a major puzzle until it was solved. And in fact, the solution is very simple. You don't have just to think about a little bit of physics. In fact, at the time that the neutrinos emitted, this blazar is not a classical blazar. And the reason is simple. You see, how do you make neutrinos at Fermilab? Back to this picture, you put a target into the proton beam and then you produce neutrinos. Well, at the time neutrinos are produced, you put a target into the jet of the active galaxy. To produce neutrinos, you don't just need an accelerator, which the astronomers were modeling. You need an accelerator with a target in the beam. And when the target is there, the source is slightly opaque to gamma rays. And so this is simple physics, totally normal. Is it true? Well, you remember the picture of the black hole 2 years ago, made by making radio interferometry pictures of the black hole. The radio interferometry people started making pictures of this black hole in a similar way, and they discovered something very interesting. They, of course, discovered the jet, but here, if you look at this was the big conclusion here, if you look at the bottom of left of my slide, they found that very close to the black hole, the jet suddenly lost its collimation. So the jet ran into something. And of course, the obvious conclusion is that it found some kind of target that it then used to produce the neutrinos. But if you have a target that's thick enough to produce neutrinos that can be seen by IceCube, there is no way that it can be transparent to gamma rays. In fact, the Fermilab target is not transparent to gamma rays. You get a neutrino beam. Everything else stays behind in the target. So there were actually 2 collaborations who did this. And so here you see the idea is that you look at the source with a set of radio telescopes and by interferometry make a picture. And one of the papers claimed that there was actually of 2 jets interacting with each other and speculated that this galaxy was merging with another galaxy. This is not a rare event. This happens rather frequently. And so that the other galaxy was producing the target to produce the neutrinos. Astronomers who are much more conservative, they usually think that super massive stars in the host galaxy can cross the jet. And this is the way then they block the photons. In fact, this picture was confirmed by our own data. Nobody paid attention. This is the TV emission, the flux, measured by magic. So these are TV gamma rays. Well, they observed 100 GeV gamma rays, but because this galaxy is so far away, these originated from TV gamma rays. And they looked, in fact, all telescopes looked, MAGIC, HES, and Veritas, looked at the time the neutrino was emitted and found nothing. This is an upper limit. It's only after 5 days that the flux slowly turned on. So again, this conclusion that while the target is in the beam, you don't get the gamma rays. This was further confirmed by an optical telescope, which had quietly been observing this source actually since 2005. And what they actually see is that the blazar switches from the off to on state 2 hours after the neutrino. So same conclusion as magic, but in optical, it happens after 2 hours, not after 5 days. So here is their, it's the master robotic network of optical telescopes. And this is the abstract of their talk. By the way, this is a 50 sigma effect. So what it actually means, I won't go into in detail through their data. You can see, let's look at the bottom picture. They have been taking data since late 2005. And the green line is what they see. And they see basically nothing, except at 2 times. They see something around 2015, which is the end of our 2014-15 burst. But then most dramatically, the most dramatic, after looking at this source for 15 years, the most dramatic thing that ever happens to this source is 2 hours after the famous 2017 neutrino was emitted. And this is the time variation of the flux times the signal to noise. You can look at their data here. You see it's this jump 2 hours after the neutrino was emitted. The reason they didn't publish this initially is, you can see here, they spent years taking data to confirm that their detector was stable and didn't do these weird excursions by accident. And so they then went back to their data in this perfectly calibrated detector. So we can now conclude with some confidence that IceCube neutrinos are detected from temporally suppressed blazars. So the fact it's a blazar, the astronomers tell us it's an accelerator. The fact that it's suppressed in gamma rays tells us it's a neutrino source at that time. In fact, we have a second event that we have been publishing very carefully. And the second source, suspected source, is this source, PKS 1502. You know, these telephone numbers just are catalog numbers of active galaxies. So it's another active galaxy, pretty much the same as TXS. It's even further away. You see the event here. It's a 300 TeV event. In fact, this event and the 2017 I've been talking about are the highest energy event alerts we have measured. And the radio astronomers pointed out to us, of course, this we found the neutrino aligned with this galaxy, and then the astronomers pointed out that this galaxy had an increase over the last many years of its radio flux, and the same as TXS. You see the radio flux increasing TXS over the years. Well, here, there was a neutrino, and again, it came at the height of, in fact, it here came at the maximum of the radio flux. And if you look at the gamma ray flux at the same time, you see the gamma ray flux goes down and reaches a minimum when the neutrino is produced. So again, you see the target moving through the beam. Close to the peak of the radio flux. It's just like TXS. What's next? Well, let me actually go back to my conclusion for a moment. So we have to now identify what the target is. And, you know, we got confused about using blazar models, but you have to think about physics, not just astronomy. So multi-messenger astronomy is, to quote Einstein, subtle but not malicious. We have some intriguing other events, including a tidal disruption, possible tidal disruption event. I'm running out of time, so I'm going to conclude. The next attraction is actually to identify gravitational waves with LIGO. We are working at that with LIGO long before they discovered mergers of black holes. That's hopefully our coming attraction. And hereby I conclude. The conclusion is obvious, actually. The important thing is neutrino astronomy exists. We need more neutrinos, we need better neutrinos, higher resolution, and various groups in the world are working at that. We are applying to build a 10 times bigger detector. There is a similar effort in the Mediterranean and one in Lake Baikal. And I think we are finally some kind of mechanism that we are closing in on the cosmic ray sources and hopefully can, after 100 years, identify them. I'm a theorist and didn't do this by myself. So this is the collaboration. And I don't like them like this. I prefer them like this. And thank you for your attention. Are there any questions?
So thank you a lot for the very nice talk. It was really entertaining. So I got a couple of questions from the YouTube, so I'll start shooting them, and then people start to make more questions. So the first one is the beginning of your talk, I mean, and also by then, you mentioned that the gamma rays which are produced, they are somehow blocked. And the question is, what is the length scale for this decay? I mean, for the very high.
Well, it depends on the energy, right? It depends on two things. You just have to think of it as the universe is opaque to these gamma rays. And what the length is they can travel depends on the energy and on how far the source is. If the sources were in our galaxy, we could actually see them, right? And so there is no single answer, but even nearby sources outside our galaxy, PV gamma rays don't get here. So you just have to calculate the transparency of the galaxy to that energy photon. That's what the calculation does.
Francis, if you allow me, if you go back to your slide where you show the Terra Incognita, the shadow in that slide gives exactly the...
Yes. I have to go all the way back, but I can keep answering questions. Why? But yeah, in fact, it's the absorption length, right? Yeah, I realized that I didn't want to go back, but I will now. Okay, go ahead. There are more questions.
Yes. So, one student, Guilherme, is asking, what's the current state of exotic neutrino scenarios, such as sterile neutrinos? So that's one question.
Yes, of course. I apologize. I just talked about, you have to realize IceCube is doing a lot of things. Here. Look, the answer to the previous question. You see here, that tells you how deep we can look in the galaxy as a function of the energy. This is, here you see, this is 100 TeV here, and we can only look 1/100th of a megaparsec, so 10 kiloparsec. There are no sources there. So here the galaxy is completely opaque. But then if you go far away, of course, even this photon has an energy of a TV, one TV, and it cannot, sorry, and it cannot reach us from faraway sources. So this represents the opacity of the micro. Think of the microwave background as a medium, and this reflects the opacity of the medium to a photon.
Okay.
And the higher the energy, the farther away it has to come from, the worse it is. Simple QED though. This whole experiment run by QED, by known standard model physics. We don't have the challenge Auger has, for instance, of having unmodeled physics. Of course, we wish we did, right? It's amazing. We now are at 10,000 TeV, and we don't see any deviation from standard model neutrino physics.
Okay.
So, second question, IceCube, of course, does lots of other things, including glaciology, its geology of the Earth, etc., etc. We have a sub-detector that was built at the bottom of IceCube in the center, where the threshold, the IceCube threshold, is something like 100 GeV. And so we are not sensitive to neutrino oscillations. You have to go to 1 GeV. So we are trying to get there, but we can now already get to like 5 GeV. So we do oscillation measurements at higher energy. And I don't have the slides here, but our next release, we are improving the reconstruction of neutrinos in our next data release on oscillations, which will be within a month or so. We'll have a determination of the neutrino parameter, oscillation parameters, that's totally competitive with nova and T2K. We haven't unblinded it yet. It may blow up in our face, but if everything goes well, we should have a sensitivity in our next analysis, similar to the long baseline experiment. But you realize we are doing this measurement at 10 times higher energy. So it's again a handle to discover new neutrino physics.
Okay,
so although I'm not working on that, I'm very excited about it.
Yeah, thanks a lot for that very detailed explanation. So I have now a question from Gustavo Figueiredo. So first, he thanks you for the very nice lecture. So actually he has two questions. First, he asks, what's the status of the cascade-like events in the IceCube in the high energy regime, say between 500 GeV up to 20 TeV?
500 GeV up to 20, oh yes, yeah. I usually talk about that. I took these slides out this time. Yeah, you see, I explained, let me explain what I think the question is. You know, I showed that, in fact, I may go back there. That's the easiest way to do this. It's not that far off. I showed that the energy in neutrinos and gamma rays in the universe was the same. If we actually study our neutrino spectrum in more detail, you see, look at this. This is the classical neutrino, muon neutrino to the Earth flux. It's actually that type of flux I use to prove that two are the same. But you see, these events here in this energy region seems to stick out. And so if you took this seriously, which there's no reason you shouldn't, the energy neutrino is actually higher than in gamma rays. And that's not a surprise either, because if the neutrinos are emitted from sources where the gamma rays lose energy, they may already cascade, lose energy inside the source, which I showed you at the end of the talk they do, and then they end up at energies that are not seen by Fermi. So they are sitting at MEV energy or at X-ray or even below that.
I see.
Right? And so this is referred to as hidden sources. So what you would conclude from this picture, if you really fitted this and looked at the slope carefully, you would conclude that there are hidden, the neutrino sources are partially hidden. And there is actually a big a movement now to try to build an MEV satellite that's look at the MEV region rather than the GV region. So this is one of its goals.
Okay, thanks. So Gustavo has another question. I mean, he's wondering, I mean, he's asking out of curiosity, I mean, how hard would it be to actually do this experiments from IceCube in a lab instead of doing it in the ice? I mean, would that even be possible to do something like that?
Wait, I'm sorry, I couldn't hear very well.
I'm sorry. Yeah, I'll repeat.
No, try again. Yeah.
Yeah, Gustavo. He also asks, I mean, how hard would it be to do the IceCube experiments in a lab? I mean, not in the ice, but in a real lab. I mean, would that even be possible?
Ah, in a lab? You mean like at the surface of the Earth?
Yeah, like in Kamiokande or something like this.
Yeah, we went through that exercise long time ago. And in fact, there was an Italian proposal to do this. You could build a particle detector at the surface, and if it's good enough, you can reject a large background of cosmic ray muons, right? You can do it. It was called Shingao, actually, and I remember the name. It cost about $10 billion in 1990 something.
Okay.
So I think this cost a lot less.
And also now I have a curiosity. I mean, you mentioned by the end of your talk you're thinking about expanding IceCube. I mean, I guess you mentioned that. So what exactly are your plans? I mean, in which direction would you like to expand it?
It's very simple. We basically do the same thing, but now that we understand the ice much better, we can optimize the detector. We were too conservative by placing the strings at distances of 125 meters. So we are going to double the distance. And if you double the distance between the strings, so you deploy the same number of strings, we will put more modules on each string and make them longer. So we now know we can space the strings by 250 meters instead of 125. So we are going to get twice the volume, 10 times the volume.
Okay, well, that's interesting. So
for the same price. Exactly.
Okay.
The detector costs the same as IceCube, but we'll have 10 times the volume because now we know what we are doing. It's not, you know, a shot in the dark, which IceCube was.
Oh, yeah.
People should not forget that we had no idea whether we were ever going to see a cosmic neutrino.
Yeah, I guess it's true. So that's interesting. So we have a question for our colleague Agostinho. So he's asking, out of curiosity, what type of measurement are you planning to do together with LIGO?
Oh, no, we actually, even before, as soon as LIGO started taking data, we actually matched our data and looked where, you know, there was any correlation between the noise in LIGO and noise in IceCube or neutrinos in IceCube. to detect possible supernova explosions or something like that. Of course, merging black holes, it's unlikely that it ever produces a gamma ray or a neutrino. But of course, what we are really interested in is merging neutron stars. And we saw one event. That event, the jet, merging neutron stars, make a jet similar to the jet of an active galaxy. And it hopefully, presumably, produces, according to modeling, produces neutrinos and gamma rays. And some gamma rays were seen in the first event, but the jet didn't point at us, so we couldn't see the neutrinos.
I see.
So we need a neutron star merger pointing at us. That would be very, and a 10 times bigger detector.
Thanks. So there's another question from Gabriel. So he's wondering, I mean, if you can correlate, let's say, the superenergetic neutrinos with other experiments like Pierre Roger or something like that.
Oh yeah, as you know, I skipped like 3 years in my life when we were doing nothing else but that type of thing. We have published papers where we correlate our neutrinos with Auger and with TA, with Hawk. We are about to do an analysis with Lasso. We have done, we've tried everything. And of course, you can try like to take sky maps of blazars or anything you can think of, star-forming galaxies, and see if there is any correlation between the neutrino map I showed and these astronomical maps. And this fails. None of these things work. And I think we have some insight. You see, if really there's no point matching with all the blazars when there are a few special blazars that are neutrino sources, then the correlation won't exist. And I think that's the situation we were in. And of course, these multi-measure astronomy and live signals, the live alerts that we sent, avoided the problem.
Okay.
It at least managed to find one interesting source.
Okay, thanks for the very detailed question. I can imagine how the hard work went through.
Well,
so now
it was very unsuccessful. It still is. We're still trying this.
Now,
yeah, we are trying. Of course, another thing I didn't talk about is we are sure we can see galactic sources. The problem is that even after 10 years, we cannot reach a 3 sigma level. So again, you need a bigger detector.
Yes,
and
so
the detector they are building in the Mediterranean will be ideal for that.
Okay, I see. So I guess my colleague Victor, so he's also in the call. Maybe he wants to ask you a question as well. So
go ahead, please.
So, hi friends, thanks again for the very nice talk. It's implicit in your talk the effort of a decade-long collaboration working to first build the detector and then calibrate and then understand the data. In one point in your talk, you mentioned that the event was confirmed by 3 different analyses. And I'd like you to comment a little bit more on this human effort of a long decade experiment to go from building the detector up to producing so important results. I know you value that very much. That was along your talk, but if you can comment a little bit longer about that, I would thank you.
We have a very unique collaboration in the sense that we are 300 people, roughly. And 300 people is, it's not a really big experiment yet. We know everybody. And it's the experiment, I always say the experiment is amazing in the fact that everybody still has lunch and dinner with everybody else. And the senior people, we have been together, many of us, since, remember the suggestion of Amanda came in 1987. And some of us started actively working on proposing the experiment around 1990. And so we have been together for 30 years. And that has worked very well. And the number of senior people are actually very few. I mean, you saw from my picture, most of the collaboration are young people. They're overwhelmingly students and postdocs. And so when we have a collaboration meeting, you know, more than 200 people attend. And you attend the collaboration meeting, you give a talk, it means you are actually actively doing something, like analyzing data or preparing for the next detector. So I think this collaboration is pretty unique in that sense. Does this answer your question?
Yes, thank you. Thank you very much.
So thanks, Francis, once again. So maybe, I don't know if Ion, my colleague Ion, has also a question for you.
Okay.
Yeah, hi, Francis. Can you hear me?
Yeah, I can hear you, no problem.
Yeah, okay. So I actually have a more, perhaps going back a little bit to the science, and actually related to this plot you're just showing. It made me think about a few things. When you show these fluxes of neutrinos, astrophysical neutrinos, you are including there events which probably come from transient phenomena, right? Like flares and things like that. Like you showed at the end of your presentation that probably some of these neutrinos come from transient phenomena. So how exactly would work to compare these kind of fluxes to other experiments like gamma ray experiments, if we have to compare events that perhaps don't happen at the same time, right?
Well, I understood your question. Oh, so, okay, let me try to answer it. And if that's not the right answer, tell me. So you are looking at the sum of all the neutrinos of a given energy in 10 years now. We actually have a totally separate analysis, which I didn't talk about, where we look for sources as a function of time, like we did with the TXS source, where we search the whole sky, but we don't search for an excess of neutrinos in that direction. We search for an excess as a function of time. And in fact, we are about to publish the 10-year equivalent of the time-independent neutrino map of the sky as a function. We are about to publish, you know, an image, a neutrino image of the universe that looks for flares over the whole sky. And that paper is about to come out. So up to now, we have only been correlating, especially these neutrino alerts which we send. We send about 12 alerts per year that we are pretty convinced are cosmic neutrinos. And the only correlation with other wavelengths as a function of time has been for those alerts. They, of course, come at a given, these neutrinos come at a given time, and then everybody looks at that time. We have also been looking, like the tidal disruption event I mentioned, which is at the moment, I cannot show it because it's being submitted to a journal that has an embargo. That event was found many days before the optical flash was found many days before the neutrino alert. And so we look typically over time scales of 1,000 seconds.
Okay, thank you. Yeah, no, I understood.
Does that answer your question?
Yes,
Yeah.
Very much. Thank you. If I'm allowed, just another quick question. Since you mentioned about galactic neutrinos, I'm very much interested in galactic sources, especially in the galactic center. As you perhaps know, the HES collaboration a couple of years ago showed that in the galactic center, probably there is a pevatron, so a source producing PeV cosmic rays in the center, and we detected 10 PeV gamma rays coming from there. Are there any news from IceCube from neutrinos from the galactic center?
Yeah, I'm very well aware.
Yeah, can actually IceCube see the galactic center with a high sensitivity? Or?
No, we cannot see the galactic center. Antares can see the galactic center. And because we are so much bigger, at the moment, we are actually similar in sensitivity to Antares. And so, in fact, this is not a competition. We do common analysis to get the maximal sensitivity. And unfortunately, the neutrino flux from the galactic center that corresponds to the HES source is too small at the moment. And I have not checked this, but I'm rather sure the next generation experiment will be able to see this source. Yeah, I'm following this with great interest. I saw your recent paper. I read it.
Thank you very much.
So we have another question from the YouTube here from Andres Delgado. So he asked if you can distinguish astrophysical neutrinos from the same direction of an extensive air shower.
No. In fact, we are looking at the right plot. Look, you may ask, how do you know this is a cosmic neutrino when this, when the background of atmospheric neutrinos is almost a factor 10 larger. So what we do is, so in fact, what we do is when the neutrino, a neutrino that comes with an air shower, it may interact inside the detector. These are all neutrinos interacting inside the detector, these black crosses. These are the ones through the Earth, right? So where are the rest of these neutrinos? Well, there are an atmospheric neutrino interacts in the detector, but it comes with muons, atmospheric muons. So we throw those events out. So we have a veto against neutrinos that come in air showers. And that allows us to measure this flux, even when the atmospheric flux is larger. Now I shift. There's another answer to your question. We have an air shower array above the experiment called IceStop. And then there is a group of people, I should have mentioned by this time, who actually are only interested in the question you ask. They look for neutrinos and muons in IceCube in coincidence with air showers in the air shower array. And between the air shower measurement and the muons in IceCube, we can do measurements of the composition. And so this ice-top array works basically between, it starts just below the knee and ends close to the ankle. So it has a very interesting coverage. It's one of its goals is to try to find where the extragalactic cosmic rays come into the spectrum. But it also measures the composition in that area. So air showers are important for us as a veto to see the neutrinos and as a signal to do cosmic ray physics with ice-top.
Okay, it's clear. Thanks for your nice answer. So I guess I just asked another of my colleague, Luis Agostinho, if he has a question to direct to you in the call. So I don't know if he wants to ask for the last question.
I am willing to stay as long as anyone has questions, no problem.
No, thanks for your time.
No, exactly. I just want to congratulate Francis for such superb talk. I mean, it was really nice. I have learned a lot. Thank you very much.
So I see no further questions in the YouTube. So I guess thanks for your very wonderful talk, Francis. I guess it was really nice. So
it was a pleasure.
No, it was our pleasure hosting you, and it was really nice. I've learned a lot, so I guess it was great. So I guess I'll just now, so thank you once again. I'll just now stop our stream on YouTube. So